Hello, my name is Josh Rack, and today I'm going to explain to you the differences between hydrophobic and hydrophilic. So, I actually found a nice little site on Chembam and what the difference is between hydrophobic and hydrophilic. So, a little bit of background that they actually gave me is that the word stem hydr comes from the Greek word of hyoder, which quite literally translates to water. So if you add hydrophobic to it, it quite literally translates into water fearing, which means it doesn't mix with water, whereas hydrophilic, which literally translates to water loving, um, has a tendency to be wetted by water, right? So some good examples of a hydrophobic material would be, say, like paper towels, um, washcloths, rice, stuff like that. Um, and all those things will absorb the water. They're what we would call hydrophilic, or water-loving materials, right? Good examples of hydrophobic materials would be something like a waterproof jacket, aluminum foil, lotus leaves is another great example of this, and these are some of the ones they actually give us. Um, and which was really quite interesting when I learned about that. And so what it actually goes into is that what it quite literally goes into is that in the last little bit of this, I'll read it to you word for word because it's quite interesting. So it says hydrophilic molecules have an affinity for water and tend to dissolve well in polar solids. Molecules that charge polarized form hydrogen bonds and or exist as ions in solution tend to dissolve well in water because the charges can be stabilized by surrounding the molecules with polar water molecules. In contrast, nonpolar molecules such as oil do not have an affinity for water. It's more desirable for the oil molecules to stabilize each other via van der Waals forces, which is something we also learned about. And the water molecules stabilize each other via hydrogen bonding. So basically what that's saying is that there are certain substances, such as, like we gave earlier, rice, um, paper towels, stuff like that, that solve better with water, right? They absorb it better. They bond with it better. Basically, is how I would word it. Um, whereas such things like, it gives the example here as oil, it doesn't bond well with it, right? So that's why some people say, that's why you hear the saying, oil doesn't mesh well with water, or however it goes. Um, and so one of the questions we actually have for this for this assignment that we have done, is it says, what is the means about how the substance will interact if placed in a beaker of water? So if we're talking about a quite literal beaker of water, if you fill it to the top, it will actually, um, from what we read, it'll basically it will bow out, right? Up until a point. So you can, as long as you keep putting a little drop after little drop after little drop, what you will actually see is, you will see it form um, a dome shape of sort, because it wants to keep interacting with its own water molecules. But if, let's say, instead of just doing drop, 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 you eventually just say pour more water into it, that surface tension is going to break it, and then what it's actually going to do is spill out off of it. And so what I feel is that if you were to do that, at first it does become hydrophobic, but that's only if you're doing it, say, drop by drop, or it becomes hydrophilic, which means it goes drop by drop by drop by drop. But then if you disturb that frequency of it, if you just say, you break the tension of what it is, it then becomes hydrophobic. And so that's what I feel, and that's what I've kind of learned about this. I think it's quite interesting. There's a little bit more to it than that, but I hope that is a good enough explanation for you. You have a great day.